So, welcome everyone to lecture number 9 in the lecture Mathematical Statistics in the winter term 23-24. I would like to begin with presenting you the one new question for the list of exams questions according to the last lecture, so there's only one question, and it's question number 11. Formulate a result concerning the strong universal consistency of the kernel density estimator and show that this result follows from the weak universal consistency of the kernel density. And as a hint, you have given the inequality of McDiarmid in its formulation, and you just have to apply this inequality of McDiarmid to show that the L1 error minus the expected L1 error matches the SVD combination. Okay, that's the first thing. Second thing, I would like to show you a slide concerning what we did the last time. That's here. And it was just we proven this theorem 3.6, which I just talked about, which is the proof is on the list of the exam questions. It's about the strong universal consistency of the kernel density estimate. Sorry, I have to confess, I don't really know whether I should say estimate, kernel density estimate, or estimator. In English, maybe the kernel density estimator is correct. So one is in German, one would be Kernschätzer, and the other one would be Kernschätzung. And don't know is the correct English word for it. Check it with one of the books. I think both are used now, but one is more usual than the other. So I use both in this direction. So you let Fn for x be the kernel density estimate with an IF kernel, and bandwidth aging greater 0, where the bandwidth satisfies the usual condition, that is the bandwidth converges to 0 for sample size tending to infinity, but not too fast in the sense that n times the bandwidth is power d converges to infinity. And then the one error of the density estimate goes to 0 almost surely for sample size tending to infinity, regardless of the density of x. And we have proven this by using the inequality of McDiarmid, which is theorem 3.7, or was theorem 3.7. You have independent R valued random variables Z1, Z to Zn, where capital A is a subset of Rd. You have a function f from a with exponent n to r, which has the property that if you change its value in one of the, or in the ith component, then the function value changes in absolute value and most by some constant ci, and that holds for all components, for all of its n components, and then the probability that f of capital Z1 to Zn minus its expectation is greater equal than epsilon is less than e to the power minus 2 epsilon squared divided by the sum I equal 1 to n ci squared. And this holds for all epsilon greater 0. It also holds if you replace f by minus f, which is clear because minus f satisfies the same assumption as f. And we have proven this one by using lemma. So this one is a modification of the inequality of Höfting, as you can see, because you can derive the, or it's basically a sharpening of the inequality of Höfting. You can derive the inequality of Höfting from this one by choosing f as the sum of the Z1 to Zn. So f of Z1 to Zn is the sum of the Z1 to Zn. And we proved this one by sharpening of the exponential bound or the exponential moment, which we use for Höfting, and this sharp-rounded bound is lemma 3.8. You have a function, you have random variables v and z, where the conditional expectation of v given z is 0, and where you have a function h, such that h of z is always less equal than v, is less equal to h of z plus some constant c. Here, v is real valued, z is Rd valued, and h is a function from Rd to R, and c is greater 0. It's a bounded function. And then you have for all s greater 0 the conditional exponential moment of s times v. So the expectation of e to the power s times v given z is less than e with exponent s squared times c squared divided by function. And we have been stuck in this proof. So I did not finish it completely, but there's not much left. What we have to show, and that's the first thing which I do in the sequel. We finish the proof. And what do we have to show? So it's proof of lemma 3.8. And still to show the following. This was relation star star, and relation star star was we had some random variable v sub n defined, and v sub n is no, it's not the proof of lemma 3.8. We have to prove, we have proven this completely, but what is left is the what was here? What was left was the inequality of the diamond. Let me show you something of this. It's 0 and 3.7. And what we did, we looked at this f of z1 to zn minus its expectation, and rewrite this as a sum, where the i's term is the expectation of f of z1 to zn given z1 to zi, conditional expectation, minus the expectation of conditional expectation of f of z1 to zn given z1 to zi minus 1. So it's a telescope sum, and we have this here for the first term. We have to show the expectation of f of z1 to zn. Maybe I turn this off for a moment. Later on. Given z1 to zn, that's the nth terms in this one minus the expectation of f of z1 to zn. Given z1 to n minus 1, this guy. And for the first one, the term inside the conditional expectation is random with respect to the random variable unconditioned. So this is just f of z1 to zn. And for the last one, I keep the last one as it is. This one satisfies show. This one. The conditional expectation of this one is times Vn given z1 to zn. This guy is less equal e to the power squared cn squared. And this was in the last time on the backbone relation last time. I still have to prove to finish the proof of the mechanical inequality. And not surprising, what I do is I use what we have. That was the reason why we have derived lemma 3.8. I use lemma 3.8 for it. So I replace v by vn, and then z is z1 to zn. No, I think there's a typing. Typing, but there's a mistake here because I did not condition on z1 to zn. I conditioned on z1. Yeah, it's correct here. It's a condition on z1 till zn minus 1. Sorry for that. Yes, n minus 1. So I will use lemma 3.8 proofs, and here I will replace v by vn, and capital Z is the vector of the z1 to zn minus 1. And then this is an n minus 1 value general variable, so d is n minus 1. And now we need to ensure the assumptions. And as you see, I need two things. I need to define this h, the function h from Rn minus 1 to R, where I plug in z1 to zn minus 1, and then h of this value is the lower bound of v, and h of this value plus some constant, and the constant will be cn, is an upper bound. And I need the conditional expectation of v, and given my z1 to zn minus 1 is 0. And that's what I start with. If you look at the conditional expectation of Vn, given z1 to zn minus 1, and then you just plug in what you have for the definition. That's the conditional expectation. And the conditional expectation is, so you plug in this value, then the conditional expectation is linear, so almost surely it's the same as the conditional expectation of the first term minus the conditional expectation of the second term. The conditional expectation of the first term is f of z1 to zn. z1 to zn minus 1. And the conditional expectation of the second term is the conditional expectation given z1 to zn minus 1. It's a function, rational function of z1 to zn minus 1. So if I compute again the conditional expectation given z1 to zn minus 1, then it's just this function. So this is this one. And then you see the whole thing is 0 almost surely just because this whole conditional expectation is only defined option. That's the first part. The second part what we need is now we have to define our function h. And what do I use for h? And h should be a function of n minus 1 arguments, which are the values of z1 to zn minus 1. And I throw this off again. Don't need that moment. And it should be a lower bound of V sub n. U sub n depends, and it should be a lower bound if I replace the values z1 to zn minus 1 by the random variables, capital Z1 to capital Zn minus 1. And this one, Well, this is a function of z1 to zn minus 1 and the additional random variable zn. And this one, as a conditional expectation given random variables, is a function of this random variable because it's the factorized conditional expectation given the value of this random variables where you plug in the random variables. And that's what I use here. But what is missing is that n, but I just make the infimum over all set in R of f of z1 to zn minus 1 set minus the conditional expectation of f of 1 to zn given z1 equals more than 1 and zn minus 1 equals more than 1. So this here. And clearly, this is a lower bound of, so if you plug in here capital Z1 to Zn minus 1, this will be a lower bound of our Vn. And to see how much it changes if you replace the value of one of the Z1 to Zn minus 1. By another value. I use a different, I first look closer at the conditional expectation. The conditional expectation, you have a factorized conditional expectation where in the random variables, you have first random variables where you have given the condition the values, and addition independent random variables. And then you know from probability theory, this is the same that if you just replace these random variables given by its values and compute the total expectation. So because of independence, that's the same as infimum R just minus the integral, and this conditional, this total expectation. Then, if I fix the values of Z1 to Zn minus 1, I can just use the integral with respect to Zn. And now comes the technical step. Yeah. Now, you look at h of z1 to zn minus 1. Then you see h of z1 to zn minus 1. Zn minus 1. That's this infimum over z of r. Then I can use this as a lower bound if I just replace this infimum by the random variable zn. And if I plug in the random variable Zn, then I get Vn. And now you can look at how much does the value of h of Z1 to Zn minus 1 changes if you replace this random, this point, whether infimum or some fixed point, by some random point. And we had this assumption. Let me show you this assumption. Star, this was called star in the last line. We mark the star here about the supremum over Z1, Zn, Zi prime of f of Z1 to Zn minus f of Z1, Zi minus 1, Zi prime, Zi plus 1 onto Zn. And that is different as it was Ci. So if I replace the last value by some random variable, then the different value goes Cn. So you know that if I add here Z1 Zn minus 1 Cn, then I get cover. And this was the assumption star. And now you have exactly the assumptions of lemma 3.8 satisfied, and then you can apply lemma 3.8. And lemma 3.8 gives you exactly this upper bound. For application. That was the star. If you don't see it, I can show it again here, but I can't see it, show the blackboard at the same time, unfortunately. Sorry for that. So we had this h defined, we had the v defined, we had h of z as equal v as equal h of z plus c, c was cn. We had the conditional expectation of v given z equal to 0. I've just shown this. And then we get the bound of expectation of e to the power s times v given z, which is just this expectation of e to the power s times v and given z1 to zn minus 1. And we get this upper bound e to the power s squared times c squared divided by 8 with c divided by c. And that's it. Questions so far? Questions, then let me quickly clean some part of the blackboard. And that's the end of chapter 3, and we start with chapter 4. chapter 4 is about point estimation. And then first introduce the problem, and now we are, so we started the lecture with something about non-parametric statistics, and now we are in the classical parametric statistics. So I start with the more modern statistics. The results were basically from, 1990 or something like this, up to 1995, something like this, and now we go back to the 1960s. Or even before. I'll start with some introduction. I just introduce the problem, which we will get up. What is our estimation problem? Well, we have given, as before, realizations of I and D random variables x1 to xn, with values in some z, which I call calligraphic x. Realizations. x1 to xn of I and D. And the variable is x1 to xn. Values in the set. This could be real numbers, or mostly it will be real numbers, or sometimes it will be also some vectors of real numbers. That's the same as before. We have given a sample of our distribution, but this time we know the class of distribution. So we have given a set or class V theta, and capital theta of distributions. Is the property that this distribution of our samples, or the distribution of x1, is in the set. So that's equal to theta or some. So we have some fixed value. And we want to know something about this parameter. And the parameter could be a whole vector, and maybe we are just interested. So, like for a normal distribution, it could be consisting of expectation and variance, but maybe we're looking just at some of its components. Maybe just look at the variance. Therefore, I also define a function g from theta to r in power. In most cases, theta will be just the real numbers, and this function g will be just the identity, and k will be 1. And the aim, we want to estimate g of theta. And your estimate is some value of your given sample. then you have some function t, and, which is the function now from, well, you plug in your sample, your the random variables in the sample takes values in your set calligraphic x, so it's x to the power n, and that should be, well, g of theta is a value in R k, so that should be R. And in principle, in the way I formulated the mode, it's still total generally, because you could use for this set of distributions, you could use the set of all distributions which exist and index them by the distribution itself. So the parameter is the distribution, but that will not be what our case is. Usually our theta will be some value of R with some exponent. That is no longer possible. Let me give you an example. We look at theta equal to R plus R plus. Then the theta has two components. I call them U and sigma squared. In the distribution, this parameter U sigma squared is just a normal distribution. This expectation U where the sigma squared. And then we look at G from theta to R. With G of U sigma squared. Well, I just estimated the values. And here in the setting, we want to estimate the variance of a normally distributed sample with unknown mean and unknown variance. Here we want to estimate the variance. Normally distributed sample. With unknown mean and unknown variance. And you all know already, or most of you will know already, possible estimates, or estimators from the introduction to stochastics. One possible estimator would be just the empirical variance of your sample. Possible estimate here. Here of x1 to xn is just 1 divided by n minus 1. I equal 1 to n. xi minus the arithmetic mean, for example. What we are doing now, first today we look at principles how to construct such estimates. And I will introduce U and V estimators and maximum likelihood estimator. Time is correct. Time is sufficient. Then we will. Then you have ways to construct estimates. Then the question is, what are optimal estimates? And we will see how to define optimal estimates. I will introduce 3 principles for that, and then we will try to show that estimate is optimal. Okay, questions about? Please?
I just wanted to ask, in the case that n equals 1, we can't, we would...
If in the case that n is 1, you cannot use the estimate, but in the case that n is 1, you have no chance to estimate variance. Or I don't know how to estimate. Well, of course you can just say the variance is 0, yeah? Or something like this. You can also produce an estimate, but you cannot produce any good estimating. It's clear. Usually in statistics, you cannot do much with one observation, which is not completely true. Yeah? If this observations is a whole vector, and the vector has IID components, then you can do something like this. You will see in chapter 5, when we construct statistical tests, then one of the famous lemmas there, which is the foundation of the whole theory for statistical tests in a non-Bayesian way. This is the fundamental theorem of Neyman and Pearson, and this fundamental theorem of Neyman and Pearson just uses one observation. But the trick is that in this one observation, you plug in your whole sample later on. Of course, I can just claim my own sample is one observation, yeah, and then I would ask for the variance of the components, yeah, and then it would make sense. Then to start up with this. Okay, any more questions? Please.
I didn't understand what the theta is exactly.
What the W theta is, that's the distribution, yeah. In this sense, you can look at the example. The W theta is the normal distribution, and theta is its parameters. Parameters of normal distribution, they are uniquely defined by the mean and the variance.
Yes. Yeah, I know that the normal distribution is defined by these 2 parameters, but is this, I was just wondering whether this is a distribution or a measure or a random variable.
No, the distribution is a measure. It's a measure, probability measure. That's a distribution. Okay? Any more? And you know from the introduction to statistics, yeah, you can identify the distribution with the measure, yeah? Because for each measure you find a random variable that it has its distribution, yeah, and the distribution is on the other hand a measure, and therefore I don't use these two different terms in a different way. They mean the same. One more question? Okay, we hear the clock, that's a good time to make a break. If this is the clock, then it should be 10:30, but on my this clock is probably wrong. On my clock it's 10:29, so I will go on at 10:34. Thank you. Okay, I would like to go on with the lecture. We come to section 4.2, construction of point estimates. Where's the data stage? Where is the And in the first step, we consider U and V estimators. We consider first U and V estimators. And you will see in the second one I called U and V estimators. Basically, you will see why the U estimator is called U estimator, and then the V estimator is just a modification of it. Here is assumed that G is given in a special way, and G of theta, as you can write as an iterated integral with respect to the distribution W theta. So it's an iterated integral of some function h of L variables, Z1 to ZL. And you have an L integrals, and in each of the integral you integrate with respect to the distribution of theta for one of these parameters. So we have Z1, L. And we have some H that goes from, well, the distribution W theta is a distribution which takes on values in the set x, paragraphic x, so x to R. And then you see G is R valued, and the whole thing, so in our setting before k is equal to. So I think you see us in the k is equal to 1, and I assume that G is given in a special way. And then the question is, okay, what is an example for this? For instance, theta could be the expectation of x1, and the expectation of x1, in this case L would be 1, it's just the integral of x1 with respect to the distribution of integrate with respect to the distribution of x1, which is b. So there exist examples, and we will later on see the second example is the variance, but that will come after I introduce the estimate. And now how to make the estimation? Well, it's rather easy. You estimate the unknown distribution W theta by the empirical distribution and plug in the empirical distribution in this integral. So you integrate with respect to the empirical distribution. That's your estimate. So that u sub n in the empirical distribution of x1 to xn and what I just explained, now we replace the unknown distribution by the empirical distribution and integrate with respect to the empirical distribution. This gives you the V estimators. So for V estimators, we estimate V theta W theta by UN and use the corresponding integral as estimate of G of theta. That means we said our estimator x1 to xn. That's just this iterated integral where I integrate each time with respect to u. Okay, now you have to calculate this integral, which is actually easy. And if you don't see it, you're going to see it in the following. If I consider some p-value function f defined on the set x, and I want to calculate the integral of f with respect to the empirical distribution. Well, then you can first say the empirical distribution just puts mass 1 over n to each of the data points x1 to xn. So this will be just the function value in data points x1 to xn multiplied with the mass 1 over n and then result. That's intuitively clear. On the other hand, some of the x1 to xn might coincide. So you might have that x1 is equal to x2, and then maybe the formula is not so easy to see, but you can also make it easier by using this un. You can, well, you define a linear combination of measures. By just saying a linear combination of measure is the how is function value on some set B defined? Well, you compute for each measure in this linear combination the function value at the set B and use the linear combination of the function values. And then you can say this un is nothing else as the linear combination of their measures, I equal 1 to n, and the xi. Where delta xi is the Dirac measure, the point xi. S, so that means if you look at the Dirac measure of some set B, then this Dirac measure is 1 if xi is in B and 0 is. And now it's easy to see that if you integrate with respect to a linear combination of measures, then this is just a linear combination of the individual integrals of the measures in the linear combination. So that's nothing else than 1 over n, I equal 1 to n, integral over f of z, delta xi. And that's you have to prove, but it's easy by the definition of the integral. Basically, prove this for the function which you integrate is the indicator function of a set, and it's obvious, and the rest follows in the standard way. And now you see what it is, yeah? Because the integral with respect to the Dirac measure, it's just the value of the integrand at the point corresponding to the Dirac measure. So that's just f of x. And now you apply this for your estimate. And then you see our Tn from x1 to xn. Now you just compute one integral after the other, and each time you get a 1 over n. Becomes the sum of the function value. So we basically get 1 over n. We get 1 over n times. So I get 1 over n is exponent L times the sum. 1 is equal to 1 to n until L is equal to 1 to n. And I get an h of okay, let me give you an example. We look at the V-estimator of a variance of a real valued random variable x. And it doesn't matter how you, at this point, how you parameterize the distribution, as you will see. Example. The estimator of variance of real value from the variable and we look at. First, I have to represent this variance of x1. Well, that's my g of theta. So my g of theta. That's the variance of x1, where the distribution of x1 depends on the parameter theta, and it doesn't matter what the parameter is. Could be a normally distributed random variable, but it doesn't matter. And now you can, know well, I just give you the formula, and you see that it's true. I compute x1 times x1 minus x2, where x1 and x2 are IID. What happens then? Then you have the expectation of x1 squared minus the expectation of x1 times x2. The expectation of x1 times x2 is because of the independence, the expectation of x1 times the expectation of x2. And because of the identical distribution, that's the expectation of x1 squared. So you have the expectation of the square of x1 minus the square of the expectation of x1, which is the variance. And then you see now you have your double integral, because there's nothing else than I can rewrite this as integral with respect to the joint distribution of x1 to x2, because of the independence. This joint distribution is the product of the the distribution of x1 and the distribution of x2. And by Fubini, it's an iterative integral, and because of both distribution of Itella, you get integral over x1. Oh no, I use here z, yeah? z1 times z1 minus z2 times Itella z1 Itella z2. So we have our h at that point, so L would be 2, and h of z1, z2 would be z1 times z1 minus z2. And now you can compute a re-estimator. Theorem of x1 xn. Well, L is 2, so it's 1 over n squared. Then you have two sums. For the first one, I use index pi. And 1 to n. For the second sum, I use index j equal 1 to n. And then the h of xi, comma xj is xi times xi minus xj. Okay. And now you expand this out, so you multiply out, so you have an xi squared times x minus xi times xj. The first double sum, well, it doesn't depend on j, so it's n times, this n cancels with 1 over n squared, this gives you 1 over n, and then remains the sum I equal 1 to n xi squared. And the second sum, you have this double sum I equal 1 to n, j equal 1 to n xi times xj. You can rewrite this as a sum of the xi times the sum of the xj. And then you see this is equal to 1 over n, I equal 1 to n xi. Any questions so far? You have realized what has happened with the mathematical level of this lecture, yeah? The basement below Earth, but won't be so forever. So it's if you look what we already have done in comparison with that for proofs, this is rather easy. But there will be, for maximum likelihood estimates, there will be a nice little proof. I can promise that. Not for real use things. But by the way, what we are doing at the moment, you might know that why there's the factor 1 over n minus 1 in the empirical variance instead of 1 over n. Yeah? It's because then the expectation is correct. Yeah? If you compute the empirical variance with IID random variables x1 to xn, then the expectation of this empirical variance is the variance. And that's called unbiasedness in English. We'll have this in a moment. And I guess you know the proof, yeah? And now I could ask you to prove this. And this is one of the proofs when I was young, which is 30 years ago, or something like this. This is one of the proofs where the students which did they had their last exam, their diploma exam at that time, yeah. And at the University of Stuttgart, it was an oral exam from 1 hour duration, about 4 lectures. And if one of them was mathematics statistics, then one possible question was proof that the empirical variance is unbiased. It's an unbiased estimate of the variance. And if you make the mistake that you learn for your exam until the very last moment, so you have 4 lectures and maybe the day before you still try to prove some things, yeah, then you will have no chance because you are too nervous to finish this proof. Well, basically, so that was one of the proofs where these students then came to the assistants who was responsible for the lecture and asked, how is this proof working? And you will see in a second that we actually prove this. And it will be totally trivial. So also the whole thing is trivial. You will see that as a byproduct, because what you see now, if you look at this one here, this is the same. If you look at it carefully, you see this is the same as 1 over n I equal 1 to n x I minus 1 over n j equal 1 to n x j squared. You see this if you expand the squared on the right hand side, and then you rearrange the formulas a little bit. Then you get this nice. So this is not the empirical variance. This is the empirical variance with 1 over n. And what we do next, and this also shows that for the V estimators, the expectation is not right. What we show next, we modify our V estimate to get so-called U estimators, and then we will see, just by the definition of the U estimators, they are unbiased, and will be also easy to see, we just get the standard empirical variance. Okay. So here expand the square on the right hand side. If you want to see this. So next you make a modification of the V estimator, and the modification is such that in this sum you make sure that as arguments of h, the arguments of h, you don't use the same index twice. So you sum up from I1 equal 1 to n, but then from I2 you use the values from 1 to n except I1. And for I3 you use the values from 1 to n except I1 and I2. That's the U estimator. This is a modification of the V estimator. given by, and I call this T and bar of x1 to xn. And if I remove all the terms in the sum where one of the indices is occurred twice, then instead of 1 over n with exponent L, I just get 1 divided by n times n minus 1 times n minus L plus 1. And then I make the sum. That one is still from 1 to n. I make I2 from 1 to n, but I2 is not equal to I1, and so on until IL runs from 1 to n, and IL is not equal to I1, IL is not equal to I2 until IL is not L is not equal to either L minus 1. And then I get an h of xi1 until h of xi. And the point is that these U estimators are always unbiased, and in the sense of the next definition, U estimators unbiased. And that's my definition 4.1. An estimator T is called an unbiased estimator of T of theta. If for all theta and theta we have the expectation where the distribution is for the distribution of random variables is chosen E W theta, and I use for this expectation the notation E with subscript theta of Tn of x1 to xn. This expectation would be T of theta. And it should hold for all theta. And here we computed E theta. The expectation using ID and the variables x1 to xn. Distribution, and because they are ID, I can just define the distribution of x1 that's equal to W theta. And now any questions to this definition? In German it would be Erwartungsfrei, English is nice. So it's one important property of the estimate that if you have a fixed sample size and you repeat your estimation and estimation again, and you average the result, then on the mean for sample size tending to infinity, you basically have the right value. Or in the mean without sample size. So if you use a computer estimate for final sample size with random values, then in the mean you have the right value, which means that if you use it again and again and make an average, and for average tending to infinity, you will go to come to the right value. And otherwise, you could be systematically away, and systematically away you would be for what we did here. This would be systematically away from the values, as you will see in a second. And now the point is, these U estimators are unbiased because U estimators estimators since well, you look at this expectation. And Tn is the sum. And then the claim is this expectation is T of theta. Any idea about this? How to prove this? Well, you just plug in the formula, yeah? And then what can you do? You have an expectation of an average. What do you do? Linearity of the expectation is the average of the expectation here. Then the expectation will be here. Then you have the expectation with respect to the random variables x with index I1 until x with index IR. What do you know about the random variables x with index I1 up to x with index IR?
None of them are the same. So
Excuse me?
none of them are the same, so they're independent.
None of them are the same, so they are independent. That's correct. If they're and anything else instead of independent, what about the interval distributions?
I mean, they're all identically distributed.
They're independent identical distributions, and this distribution is a distribution of is W theta. So, but then you see this whole expectation is each time the same here. So I have an average of values which are each time the same, which give you just one average. So the whole thing here is the same as the expectation with respect to theta of h of x1 to xl. And what we've used is the linearity of the expectation. The expectation. And we have used that the joint distribution of the x I1 to x IL is the same as the joint distribution of x1 to xl. So if I want to L are pairwise distinct. And that's what we have in this sum, because our sample is IID. So we are here. Any idea how to compute this expectation? The expectation with true parameter is value is theta, so the distribution of x1 is w theta of h of x1 to x. How can you compute this expectation? You integrate over the measure of W theta?
Yes, so technically you integrate over the joint distribution.
Joint. Technically you just integrate, so technical this is an integrate with respect to the joint distribution of x1 to xl. Correct.
But then you can just write it as an iterated integral.
You can write it as an integral because the independence, the joint distribution is the product distribution, yeah? And then you can apply the theorem of B. One is an iterated integral with respect to the distribution of x1 to xl, and then?
There should be the definition of G.
And that should be the definition of G, and why?
We said G is the integral, the iterated integral over some function h.
G is the iterated integral over some function h, but the integrated, the measure which we are integrating there is w theta. Where does the w theta come from? At the moment you integrate with respect to x1 to xl.
We have the distribution of x1 is w theta.
The distribution of x1 is w theta, and therefore the distribution of x1 to xl is w theta. Perfectly correct. So, but you see what is happening here. This is the so if we use B and the independence, you see the whole thing is the integral of h of x1 to xl, x1, and now I can use that EXI is just W theta by our assumption. Then you get, and I maybe I replace the capital X by small z. Then you get this integral. And this was our assumption. This is just a G of theta. it's actually very easy to prove that U estimators are always unbiased, just by definition. And now we look at the U estimator for of the variance. So I look at the example of above. Simulation. The U estimator of variance. And then you see, I call this T and bar. Well, you see, in our example, this was our G of beta, yeah? So H of, so N was 2, H of Z1, Z2 was Z1 times Z1 minus Z2. So I sum over, so I have a 1 divided by N times N minus 1. And I sum over I equal 1 to N. And J equal 1 to N J not equal I of xi times xi minus xj. So we get this one. And now you see if j is equal to I, then xi minus xj is 0. So I can omit this one here. So we get the 1 over n times n minus 1. I equal 1 to n, j equal 1 to n, xi times xi minus xj. And sorry for that guy, I just go on here. And if you look at this one, well, if you have 1 over n squared, then this is just the V estimator. So this is n divided by n minus 1 times the Tn of x1 to xn. And for Tn of x1 to xn, we have seen already this formula here. And you see we can indeed with the empirical variance xi minus 1 over n j equal 1 to n xj. And what we have proven as a byproduct is that the empirical variance is an unbiased estimate. Questions so far? So I told you last time that I was 1 minute overdue, therefore I would stop 2 minutes early. But I have to tell you, when I cut the video, I realized it was only 45 seconds too long. So I have to stop 1 minute 30 early, not 2 minutes. And I think that's exactly the time now. Thank you. See you next time.